You've known about scalars ever since you were young. They're just some kind of number that has some physical meaning, often with units attached. Vectors came a little bit later. A vector, we learned, was something with both a magnitude, often with units, and a direction. Note that in that description we never learned anything about three numbers. We never learned about an x, a y, and a z, because a vector has some kind of meaning outside of a coordinate system. It is a magnitude and a direction. You have this kind of visualization of an arrow pointing in the middle of space somewhere. Now it turns out that this idea, this defining idea of defining objects geometrically, independent of any coordinate system, is a very important one. And just as a vector can be expressed by linear combination of basis vectors in some vector space basis, we can also describe it as just an object in and of itself. And it turns out there are geometric objects other than scalars and vectors, but larger ones that in some basis are described, for example, by matrices rather than just by lists. And the general term for all of these geometric quantities is a tensor. Just as we built up our understanding what a vector was from a series of examples, we're going to do the same with tensors. So we've learned about scalars and vectors. So too, we're going to learn about more general examples of tensors. So scalars might be something like the temperature of a room, or the charge on an electron, or the mass of a black hole. Vectors might be the position of a particle, or its momentum, or the force on it. And tensors can be things like stress and strain and inertia and polarizability. And you'll note that all these examples of tensors are in fact due to the messy properties of real materials, which is where they crop up a lot. We're going to be talking about Cartesian tensors, i.e. tensors in just Cartesian coordinates. For further reading, I strongly recommend you check out the Feynman lectures on physics, which has an excellent treatment of this topic that we're going to follow fairly closely. Now imagine you have an electric field. Okay, so I'm going to write some axes, x and y. Imagine you apply an electric field to a material. So there's my electric field, which is a vector. Now when you apply an electric field to a material, real materials have lots of stuff in them, lots of atoms or molecules, and usually these things get a little bit polarized. In other words, each molecule splits up into a bunch of dipoles. And the amount that it gets polarized depends on both the material and the electric field, the strength of the electric field. Now the stronger the electric field, the stronger the polarization. And so if we apply an electric field in the x direction, then we get a polarization in the x direction. If we apply an electric field in the y direction, we get a polarization in the y direction. And this relationship I'm drawing here is linear, which means when my electric field is weak, we often get a linear relationship, and so the polarization is just proportional to electric field. Now the question is, of course, what happens when these two proportionality constants are different? Now in something that is very unstructured, that's kind of unusual, but if I was to have, say, a large number of polymers, they might have particular directions. And if they have particular directions, then you can imagine, if they're arranged in a particular way, you can imagine that they might be easier or harder to polarize in one direction compared to the other. So supposing it's slightly easier to polarize in the x direction, so that this coefficient's a bit larger than that coefficient, then what we're going to get is we're going to get an x and a y component of polarization that are different, which means, of course, that our polarization vector, P, is going to be in a different direction to the electric field vector. Now that's actually a really big step, because it means we have to re-examine our ideas back here, that when we apply an electric field in the x direction, we get a polarization in the x direction. If I applied this electric field directly along the x-axis, I might actually have got some polarization in an arbitrary direction. It could have been anywhere. So in fact, in general, I have a different relationship. So my px actually has to be a linear combination. It has to depend on the electric field in all sorts of directions. And will indeed have a component due to the x, y, and z directions of the electric field. Similarly, the other two components of the polarization will depend on Ex, Ey, and Ez. And you can see that we have a completely general linear relationship between the polarization vector and the electric field vector. And probably a better way to write that would be in vector notation. So you'd have a vector, polarization vector, is equal to some kind of matrix of alphas times the electric field vector. And this thing here is a vector. And this thing here is a vector. And this thing here, the polarizability, is a tensor. And that's our first physical example of a tensor. If the polarizability had been just a single number, just a scalar, then in fact the vector of the polarization and the vector of the electric field would have had a relationship that looked a lot like that. Indeed, the identity matrix times an alpha is a perfectly good example of a tensor. If it had been a simple vector, however, there's no real way we could have written this. There's no way we could have written a general relationship, linear relationship between two vectors by a vector times electric field. So if we're going to start having it depending on different directions, then in general we have to have not just 3 numbers, but up to 9 numbers describing the polarizability. And that describes a matrix in this basis, in this Cartesian basis, a matrix that is that object, that polarizability, which is a tensor. The key idea of a tensor is that it's a geometric object. It has some kind of meaning, some physical meaning outside of the actual coordinates that it has. So it's not just 9 numbers, it's a thing. In the same sense that this polarization is a vector, it has an actual direction, and this electric field has an actual magnitude and direction, this object here has an actual set of structure. And if we change our coordinates, if we were to rotate all our coordinates, we know we would have to rotate our numbers in this vector. We know we'd have to rotate our polarization exactly the same way. And indeed, as we change our coordinates, that tells us how we have to change the numbers in this tensor as well. So this is a thing that can be described in terms of numbers, but the fact that it's a tensor tells us how it has to transform as we change our coordinate systems. Now, unfortunately, mathematicians and physicists typically use different notation here, but physicists call a vector a rank 1 tensor, and something that can be described like a matrix like this is a rank 2 tensor. And technically, I suppose, a scalar is a rank 0 tensor. Just as a vector can turn up in lots of physical situations, like the electric field can be related to the force and the charge, as well as the polarization, so can a rank 2 tensor like polarizability can turn up in lots of different situations. The work done required to make a certain amount of polarization, if you look at the sort of differential, a certain amount of work done is going to be equal to the electric field, force per unit charge, times a little bit of extra polarization. So if you integrate that up, you find that the energy involved is a half E dot P. And of course, we know the polarization is related to the electric field like that. And so we have that the scalar, the energy, is. And so another thing that the polarizability can do is it can take 2 vectors to a scalar. So it can take 1 vector to another vector. It can also take 2 vectors to a scalar in this relationship here. And in fact, it can do all the things that matrices can do.